In this lecture, we'll discuss on the existence and uniqueness of solutions for the autonomous systems, which are described in the form of x dot equal to f of x, where x of t belongs to Rn, and f is a function that maps from Rn to Rn. The initial condition is at t equal to 0, so x of 0 is given by this x0, which is a point that is taken in Rn. Okay. Now suppose that this function f is locally Lipschitz at the initial point x0, then what does the uniqueness and existence and uniqueness result states is for such a condition of f, there will exist a positive real number delta such that there will be a unique solution xt to the differential equation that is describing the autonomous system x dot equal to f of x is the differential equation. Okay, so there will be a unique solution xt which starts at x0, and this uniqueness and existence will hold over the time interval 0 to delta. Okay, so if f is locally Lipschitz at the initial point x0, then it essentially means that you will be able to find a time interval 0 to delta. Delta, of course, is going to be a positive real number. Okay, so you'll be able to find a time interval 0 to delta over which a solution x of t will exist for the differential equation under consideration. Not only that, the solution will also be unique. Okay, so to understand what can be this delta and how locally Lipschitz condition of f at the initial point x naught helps in the existence and uniqueness, will see the proof of this particular result. Okay, so observe the differential equation x dot of t f of xt equal to f of xt with the initial condition that at t equal to 0, x of 0 is at some point x0. Now if you integrate on both sides, what you get is x of t is nothing but x0 plus integration 0 to t f of x tau d tau. Right. Now please note that the two statements that we are going to make are essentially equivalent statements. X of t is a solution to the differential equation x dot of t equal to f of x of t with x of 0 being x0. This is equivalent to saying that x of t is a solution to the the integral equation that we have just got, x of t equal to uh, x0 plus 0 till t f of x tau d tau. Okay, so if you can find a solution to this integral equation, that is essentially a solution to the differential equation with the initial condition x of 0 being equal to x0. Okay, so now observe the integral equation. We'll now stick around with the integral equation. Okay, observe the integral equation. If you see the LHS of the equation, which is just x of t, and the RHS of the equation, which is this expression that you have here, both of them are dependent on x of t. LHS and RHS, they both depend on x of t. Okay, so to solve this integral equation and find out what x of t is, we will resort to a iterative process. Okay, to solve the integral equation for x of t, we will follow an iterative process. So in this iterative process, the first okay, what is happening in this iterative process is in each iteration we will generate an estimate of the solution trajectory which will be better than its previous estimate. Okay, so what we'll do is we'll initialize this iteration. Okay, or the first step in the iteration is initialized to a function this, where t is in the interval 0 to delta, or t in the interval 0 to delta. So x1 is a continuous function such that x1 of t is identically, so this three parallel lines essentially means identically equal to, is identically equal to this constant vector x0, which is basically serving as the initial condition for the differential equation. Okay, so if I want to write it in another way, this actually is nothing but it is trying to say that x1 at every instant of time will be x of 0 for all t belonging to 0 to delta. So this is what is our first initialization. And how is the iteration defined? So for this we need to define an operator p that takes in continuous functions in the interval 0 to delta, in the time interval 0 to delta, and maps it to the set again, maps it to another continuous function that is defined over the time interval 0 to delta. Okay, so this is a set of continuous functions where y belonging to this is defined as y being a function that maps from 0 to delta to Rn, and y is a continuous function. Okay, this is what this C0 0 to delta means. That is a set of functions. These functions are continuous and these functions map from the time interval 0 to delta to Rn. Okay, so P is a operator that takes such continuous functions, that takes such continuous functions and generates continuous function back in the set. Okay, so P is operator that does this. And how is P defined? P acting on a continuous function, so y belonging to the set of continuous functions over 0 to delta. If P is the operator that acts on y, let's say the continuous function that it generates is z. This is such that z of t which is nothing but P of y of t is going to be equal to, or rather let us keep it specific to our case. So in our case, yeah, sorry, I think we can use this. So for a continuous function y from the set, z is a continuous function that is generated by the action of p on y, such that z of t is nothing but x0 plus 0 to t f of y tau d tau. This is what the operator p does. This is how the operator p actually generates. So x0 is what? X0 is the initial condition that we had used. Okay. So this is how the operator p is defined. P is the operator which is in the initial condition that we had used for the differential equation under consideration, plus 0 to t f of y tau d tau. Now with x1t as the, so x1t being defined as identically equal to x0. So x1t is a continuous function over the time interval 0 to delta, such that it remains constant at x0. So that is the first that is the initialization of the iteration, and the next initialization is essentially such that we can say it to be, so let me put it like this, for t belonging to 0 to delta, and then xi plus 1, basically the iteration in the I plus 1th step. So the continuous function generated in the I plus 1th step is p acting on xi. Okay, so we start with the best possible guess that we think we have about the solution, and that is nothing but the initial condition itself. So p acts on x of 0. Okay, so p acts on this x1 of t. P acts on x1 and it gives you the continuous function x2. So here x1 is the first guess that we have about the solution trajectory, x, or the solution to the differential equation that we have under consideration. Okay, and that gives me another estimate which is x2. Okay, so what is happening is we started with x1, p acted on x1 and give me another estimate x2, then p acts on x3, p acts on x2, gives me another estimate x3, get another estimate x3, and this continues, right? So what is happening is, as p is acting on the success on the previous elements, it is generating another estimate. And what is happening in this process is we are generating a sequence of continuous functions here. So the sequence is x1, then x2, and then x3, where x2 has been generated from x1, x3 has been generated from x2, then x4 will be generated from x3, and so on. So we generate this sequence. Okay, with p being an operator defined as this. This is the definition of p. So here z is nothing but xi plus 1 and y is nothing but xi. Okay, so with this definition of P, we keep on generating the sequence of continuous functions which are continuous over the time interval 0 to delta, and our aim is basically to be able to find a delta. Okay, so what we are aiming at is we should be able to construct a delta such that with f being locally Lipschitz at x0, the sequence that we are generating, okay, the sequence that we are generating under the action of P converges to the solution trajectory x. Okay, so now please understand one thing from here. What happens when P acts on x? If you use the definition of the operator P, then when P acts on x, where x is the solution trajectory itself, then what you will notice that P acting on x yields x back. So no matter how many times P acts on x, it will always give you back x. So here the solution trajectory x that we have is essentially a fixed point as far as this operator P is concerned. Okay, so to see how we have to construct a delta so that the sequence that was being generated x1, x2, x3, x4 and so on converges to this fixed point x. Okay, under the condition that f is locally Lipschitz at x0, which we essentially use to initialize the sequence, we need to understand a result known as the Banach fixed point theorem. Also, the iteration that we are using to finally go towards the solution trajectory x. Okay, so the iteration that we are so this is the iteration that we are using, right? Let me draw another box around it. So this is the iteration that we are using to go towards the solution trajectory x, of course under certain condition delta and f being locally Lipschitz at x naught. So this iteration is known as the Picard's iteration. Okay, so in the forthcoming lecture we will discuss some preliminary notions that are required to understand the Banach fixed point theorem. Then we'll see what this Banach fixed point theorem exactly is, and following that we'll see how this result can be used to find or can be used to construct a delta and use the condition of f being locally ellipses and x naught to show that with this iteration you will finally converge to the actual solution, and the solution that you have is essentially unique and will exist over the time interval is unique, and so basically the solution is unique in the time interval 0 to delta. So we'll stop here. Thank you.